Understanding hydrogen energy and its niche role in our energy future. Hydrogen energy is all the buzz at the coffee shop these days. But unlike the buzz one gets from their double espresso, most people don't really understand how this buzz works. This short video describes the various ways hydrogen can be generated, discusses the various market niches where hydrogen energy could have a competitive advantage, and discusses the challenges that hydrogen faces in becoming a meaningful player in a carbon-free world. Hydrogen is the lightest, smallest, and most abundant element on the planet. While pure hydrogen is a powerful carbon-free energy source, as the most reactive element God created, hydrogen loves to combine with other elements to form compounds, such as methane, ammonia, and water, to name just a few. Therefore, there is virtually no pure hydrogen on the planet. It must be separated from one of those molecules, and it takes another primary energy source to do so. In that regard, hydrogen is not really a source of energy, but a carrier and deliverer of energy. The vast majority of hydrogen today is generated through steam reformation of methane, with the primary energy source being whatever is generating the steam, usually more methane, but it could be coal, nuclear, renewables, or any other energy source. The challenge is that the chemical process of separating hydrogen from methane emits CO2, and with fossil fuels being the most prevalent primary energy source, those emissions are added in as well. Hydrogen generated from methane reformation is called gray hydrogen, while if the emissions are captured and stored, it is called blue hydrogen. A long known but little used option for separating pure hydrogen is through the electrolysis of water. It is rarely used because water is a very strong, stable molecule, and it takes a lot of energy to break those molecular bonds, requiring much more energy per kilogram of hydrogen as methane reformation. The reason it is even being considered is because there are no CO2 emissions from the chemical process itself. And if renewables are used as the primary energy source, there are no direct emissions at all. Hydrogen generated from renewables and electrolysis is called green hydrogen. Since both processes ultimately provide carbon-neutral energy, the best way to compare blue and green hydrogen is to compare the amount of energy resources it takes to provide a kilowatt-hour of end use. The end use of the world is going to do nothing but increase as the economies of the developing world advance. And ironically, it will take even more energy to adapt to higher sea levels, hotter summers, and colder winters. Therefore, the amount of energy resources the world needs to meet the end-use demand is of utmost importance. The blue hydrogen process is very efficient, providing 1 kilowatt-hour of end use for every 1 kilowatt-hour of primary energy input, including the energy required for carbon capture. Green hydrogen, on the other hand, requires almost 3.4 kilowatt-hours of primary energy to provide the same 1 kilowatt-hour of end use. Further, green hydrogen consumes huge amounts of fresh water in the electrolysis process. Despite that competitive disadvantage, proponents of green hydrogen foresee a world where we have excess renewable energy available, so the inefficiency of the process won't matter. But the inefficiency looks even worse when you compare the actual generation capacity required to serve the end use. Let's look at a situation where the end use is 1 kilowatt of demand over a 24-hour basis, 24 kilowatt hours total. A blue hydrogen facility with methane as the primary energy source could operate virtually 100% of the time, only needing to be shut down for occasional maintenance. Assuming 90% uptime, only 1.1 kilowatts of capacity would be required to provide the 24 kilowatt hours of end use on a continuous basis over a 24-hour day. However, because wind and solar only operate 25 to 35% of the time, a green hydrogen facility would need to have over 11 kilowatts of capacity available to ultimately provide that same 24 kilowatt hours of energy over the same time period. All that capacity takes millions and millions in upfront capital, tons and tons of precious metals, thousands and thousands of acres of land, and miles of gathering and transmission lines to collect all those spread out electrons. Since both processes ultimately provide the same amount of carbon-neutral energy, it just makes a lot more sense to do it in the most efficient manner possible. Now let's discuss the niche market for hydrogen energy. Most hydrogen today is used in refining oil, making ammonia for fertilizer, and in various chemical and industrial processes, while almost none is used directly for energy. In terms of potential future energy use, once hydrogen is generated, it can be burned directly as a fuel, or more commonly, it can be used in a fuel cell to generate electricity. In either the combustion or fuel cell process, hydrogen is combined with oxygen, with the only emissions being water vapor. Therefore, there are no carbon emissions at the point of final consumption. Despite the carbon-free advantage, hydrogen is not currently used as an energy carrier because it has very limited and very specific applications. In terms of powering the grid, it doesn't make sense to use electricity from a primary energy source, no matter if fossil fuels or renewables, to generate hydrogen and then to turn right around and generate electricity for the grid. It's far more efficient to put those primary electrons directly into the grid. Therefore, hydrogen's primary application will be in the transportation sector, where carbon capture is not possible at the final point of consumption. Of course, hydrogen will have to compete with electric battery vehicles, where it is currently at a significant disadvantage in terms of limited infrastructure and market share. However, because current gasoline filling stations could more easily be converted to hydrogen, that situation could reverse in the long run. The main advantage of a hydrogen vehicle are A, they weigh only a fraction of an electric vehicle loaded with batteries, B, they can have approximately double the range of an electric vehicle, and C, they can be refilled in minutes versus hours at a recharging facility. Therefore, hydrogen could eventually have the carbon-free market for long-haul transportation, heavy machinery that needs to work on a continuous basis, and possibly for shipping and air travel. In addition to the transportation market, hydrogen has the energy capacity to get to the extremely high temperatures needed to make steel, while electricity does not. So it is a potential replacement for carbon energy in high-temperature industrial processes. And finally, as proposed by the green hydrogen proponents, hydrogen could be used for energy storage in a situation where excess renewables already exist to the point that, when they are generating, the grid has no room for their electrons. Unlike a battery that slowly discharges if not used, hydrogen will have no loss in energy capacity over time. But just because renewables are the primary energy source doesn't mean you can't use methane reformation to create blue hydrogen. Even as an energy storage strategy for excess renewable energy, blue hydrogen still wins out over green, as virtually all the original energy generated is available for use, versus less than 30% for green. Again, the inefficient green hydrogen process just does not make sense. Unfortunately, hydrogen energy faces many challenges. As the smallest and least dense of any molecule in the universe, it takes up a lot of volume per unit of energy, 3 times that of natural gas. It can more easily leak out of flanges and connections, and it is small enough to diffuse into steel, making it brittle. That means that hydrogen will be a challenge to store and transport to where the energy is needed. Turning it into a liquid reduces the volume, but you have to reduce the temperature to minus 253 degrees Celsius to do so, so it is not practical. The other option is to combine it into a more dense molecule, usually ammonia, and then truck or pipe that fluid and reconvert it back if necessary at the end use. Unfortunately, the process to convert to ammonia and back is only 70% efficient, so 30% of the equivalent energy is used in the process. One solution to the transportation issue would be to generate the hydrogen where it is needed, using small hydrogen generation plants, though you would still need to store the product. But at the end of the day, storage and transportation have significant challenges to overcome before hydrogen energy will become a meaningful player in the energy mix. In closing, here are 4 key takeaways on hydrogen energy. Number 1, hydrogen is not an energy source, but an energy carrier and deliverer. To get hydrogen, you must separate it from another molecule, and it takes another primary energy source to do that. Number 2, it takes over 3 times the energy to separate hydrogen through the electrolysis of water compared to the steam reformation of methane. Therefore, even if the primary energy source is renewables, blue hydrogen with carbon capture is a much better use of the primary energy than generating green hydrogen. Number 3, hydrogen is not a replacement for the primary energy source in terms of serving the power grid. Whether the primary energy source is renewables, natural gas, or better yet, nuclear, the ultimate grid-scale carbon-free energy, it is far more efficient to put those primary electrons directly into the grid. And number 4, hydrogen's application, therefore, will be primarily in the transportation sector, where carbon sequestration is not possible at the point of consumption. With batteries being heavy and inefficient, hydrogen is currently the only possible carbon-free option for long-haul transportation, shipping and air travel, and for heavy equipment that needs to operate on a continuous basis. In the end, will hydrogen overcome its challenges to become a mainstream deliverer of end-use energy? Time will tell, I suppose. Time will tell. The end of this video anyway, if not the discussion. Please go to my Understanding Energy playlist on my YouTube channel to see more educational videos on energy. It is certainly a topic worth your time and effort to understand. No resource exists that compares energy sources based on a given amount of output energy in kilowatt hours. Therefore, the amount of energy and resources required to generate a kilowatt hour was calculated based on publicly available conversion factors. If you would like a copy of the references and the calculation spreadsheet that you can actually read, please email me at gsharp@marion.bz and I will share.